all inert gases would not like to form any reactions, and they are stable because they have 8 electrons in their outermost shell. And scientists found out that all the elements in the periodic table, especially the main, we are talking about the main group elements, they would like also to have 8 electrons in their outermost shell to be stable like the inert gases, the nearest inert gas to them. That's why all of them would tend to form bonds. Either the bonds are formed by where the elements, either they lose electrons or they gain electrons, or else they share electrons in order to form these bonds. How are you, Abdurrahman? I allowed you recording, Abdurrahman. Okay, so as I told you that all the elements, the main elements, would tend to have the electronic structure of the nearest and inert gas. So we will see that some of them would lose electrons in order to have these 8 electrons in their outermost shell, or else other elements would gain electrons. And as we know, of course, that if we look at elements in group 1, we have seen in chapter 2 that all elements in group 1 have only 1 electron in the outermost shell. And so if they lose this electron, they will form 8 electrons in their outermost shell. For example, if I have lithium, for example, it's in the simplest form, it is 2, 1. So if it loses this electron, it will have 2 electrons like that in case of helium, which is its nearest inert gas. If we look at sodium, it's 2, 8, 1. And so if it loses this electron, this means it will have 8 electrons in the outermost shell, like the nearest inert gas, and so on. Also in group 2, in group 3. But in group 1, they lose 1 electron in order to attain the electronic configuration of the nearest inert gas. That's why all group 1, when they lose these electrons, they form a positive 1 ion, and the positive 1 ion will have a full outer shell number of electrons, which is 8, and becomes more stable. For group 2, they are going to lose 2 electrons and form a +2 ion to attain the electronic configuration of the nearest inert gas. Group 3, the same. In group 4, we say that either they lose or they gain electrons. So sometimes we write them ±4, although of course we will see that group 4 tend to form covalent bonds, not ionic bonds. They tend to share electrons. For group 5, if we see, for example, nitrogen, it has 2 and then 5. It's present in group 5 because it has 5 electrons in the outermost shell, and it's less energetic to gain 3 electrons to attain the full electronic configuration rather than to lose these 5 electrons. That's why all group 5 will see that they have a -3 charge because they gain 3 electrons. For group 6, like in case of oxygen, for example, it is 2 and then 6. That's why it has 6 electrons in the outermost shell. It's present in group 6. It's less energetic to gain electrons, 2 electrons, than to lose these 6 electrons. That's why it has a -2. All group 6 will have a -2 charge. For group 7, they will gain an electron. That's why they have a -1 charge. So we say that all metals present in groups 1, 2, and 3, they lose electrons, but non-metals would gain electrons to attain the electronic configuration of the nearest inert gas. So we see that there are 3 types of bonding. We have, for bonding, we have ionic bonding, where either atoms lose or gain electrons, and then they bond together. Bond together means that they react together in order to be more stable. And the second type of bonding would be covalent bonding, where electrons are shared between atoms, as we are going to see. And the last type of bonding is the metallic bonding. Now, we start with the ionic bonding. Ionic bonding always takes place between a metal and a non-metal. It takes place between a metal and a non-metal. where the metal would tend to lose its electrons, but the non-metal gains electrons. So if we take, for example, sodium chloride, which is a simple ionic compound, we will see that sodium chloride is formed by the interaction or the reaction between two sodium metal atoms together with chlorine element. Of course, sodium is in the solid state and chlorine is in the gas state, where it forms two sodium chloride solid. Now, how does this bond form? It formed because sodium, every sodium atom of these has lost an electron to form sodium ion plus electron. Also, another sodium atom would do the same. It will lose an electron to form sodium ion plus electron. And then the sodium, and then the chlorine gas would gain these two electrons and form the two chloride ions. So if we add these three equations, we get that two sodium atoms react with one chlorine molecule to get sodium chloride as an ionic compound. Now, how does this bond forms? As we just said, that if we look at sodium, the outermost shell of sodium, it contains only one electron, as we know that sodium has the electronic configuration 281 in its simplest form, of course. It has only one electron, and the other sodium also has only one electron. For chlorine, chlorine, as we know, is a simple covalent molecule, as we studied in O level. So chlorine is formed by the interaction between two chlorine atoms forming the chlorine molecule, as of course we are going to study in more details after the ionic bonding, inshallah. And here we will see that each sodium would give its electron to one of the chlorine atoms, and then the ionic compound is formed where sodium is now empty. The outermost shell of sodium is empty, but we have to write positive charge to show that it lost its electron. And also the other sodium lost its electron and formed the positive ion. But for chlorine, both atoms gained an electron from the sodium and formed the chloride ion. The chloride ion, you see, of course, that each chlorine had at the beginning 7 electrons. Each chlorine had 7 electrons at the beginning, and it gained an electron from the sodium atom to form the ionic compound, which is sodium chloride. So this is what happened, that the sodium lost its electron and formed a positive ion. Of course, usually we show the outermost shell only, and sometimes they will ask you to show how are you, Dina?
I'm good, Miss.
Alhamdulillah. I don't know, I allowed you recording before because it doesn't show that you need recording. Okay, so as you see here that each, I don't know what's happening. We will see that each sodium lost an electron and formed the sodium ion. Of course, we don't have to show any electrons in the sodium because we are showing only the outermost shell, except if they ask you to draw all the shells. This is something else, but otherwise we only show the outer shell only, and it is devoid of any electrons because the sodium gave its electron to the sodium, to the chlorine atom, giving the chloride ion, and the other sodium also lost its electron and formed the sodium positive ion, giving its electron to the other chlorine atom, forming the chloride ion. This is in case of sodium chloride. What happens if I have, for example, magnesium reacting with oxygen, forming magnesium oxide? Now, as we know that magnesium is present in group 2, which means that the outermost shell of magnesium contains 2 electrons, and oxygen is present in group 6. It means that it has only 6 electrons. Which do we have to draw all 4? No, you can draw only 2. Yes, you mean that you have to draw only 1 positive and 1 negative. Yes, you have to show, but because here we have drawn the 4y because we have to show that chlorine is a diatomic element. So chlorine as a whole will gain 2 electrons, not only 1 electron. That's why I've drawn here the 4. But of course, if you want to draw sodium chloride, you can draw only 1 sodium ion and 1 chloride ion only. But this is what happens actually. The 2 sodium atoms react with a chlorine molecule. This is what happens actually. Okay. But for magnesium oxide, the oxygen needs 2 electrons. It's present in group 6. It needs 2 electrons. And also, magnesium can lose the 2 electrons, so it can give it to the oxygen. But also, as we did in case of sodium and chlorine, the reaction is between magnesium metal and oxygen gas to form magnesium oxide. So here also we have an oxygen molecule. Oxygen molecule means it has 2 oxygen atoms sharing their electrons together, but each oxygen will gain 2 electrons from each magnesium. We have here 2 magnesium atoms. Each of them would lose 2 electrons to give it to one of the oxygen atoms, and it forms the magnesium ion. And here we have to show that the magnesium ion has a +2 charge and that the oxygen has gained these 2 electrons. And that's why now it has a -2 charge. But also, like in sodium case, 2 atoms of magnesium would react with 1 molecule of oxygen to form 2 moles of magnesium oxide. And we have to show outer shells only. Now, after sodium forms the positive ion and the chlorine forms the chloride ion, or the magnesium shows the +2 charge and the oxygen forms the -2 charge, then electrostatic attraction force would go between these 2 ions. These 2 ions will be attracted together by a very strong force, which we call the electrostatic attraction force. And in that case, they will form the magnesium chloride ionic bond, or they form the sodium chloride ionic bond. If we look at ionic compounds, we will see that not only 1 magnesium reacts with 1 oxygen atoms or ions, or 1 sodium ion reacts with 1 chloride ion. This is not the case. In case of ionic compounds, we'll see that thousands of positive ions and negative ions are electrostatically attracted to each other. It's not only very simple that 1 sodium ion interact with 1 chloride ion. This is not the case, but they form what we call a giant ionic compound. We say that we have giant ionic compounds, where we have thousands of positive and negative ions joined or bonded together electrostatically. If we look here, as if we have a cube, we will see that we have chloride ions at the corners of this cube, chloride ions, or else we can draw a circle and then we put a key that this circle means chloride ions. And we have sodium ions in between each, of course, chloride ions here too. And we have sodium ions in between each chloride ions. Between every 2 chloride ions, we have a sodium ion. We can draw them simply as balls, small balls. We have here the chloride will be represented by a big ball like this. We'll see that each chloride will take the corner of a cube and the center of each face, and the sodium ions are in between. If this is the sodium ion, if we draw it, because sometimes they would ask you to draw a simple representation of a sodium chloride, for example, crystal. So between each 2 chloride ions, we have a sodium ion in between. And we see that for each chloride ion is surrounded, by 6 sodium ions, and each sodium ion is surrounded by 6 chloride ions. So in that case, we will see that we found that there is a giant ionic compound. We have lots and lots of positive and negative ions that are bonded together by electrostatic attraction force. Each chloride ion is surrounded by 6 sodium ions, and each sodium ion is surrounded by 6 chloride ions. Of course, when we draw this structure, we have to show that we have in between every 2 chloride ions, we have a single sodium ion. But of course, the ions are directly attached to each other. They are not separated. We draw them in this form because we want to show how the bonds are formed. But in real case, you will see that the sodium and chloride ions are touching each other. You see here in this photo, they are touching each other. They are not separated, but they are touching each other in reality. They are not separated, but we draw them separated to show that the bonds are between the green ones. The big ones are the chloride ions, and the small ones are the sodium ions. You will see that, for example, if we take this sodium ion, which is this red one, this small red one, is surrounded by 6 chloride ions, 1, 2, 3, 4, 5, and 6. And we will see also that every chloride ion, which is this green one, will be surrounded by 6 sodium ions, 1, 2, 3, 4, 5, and there is 1 because this cube is repeated in the 3 dimensions. It's repeated to the right, it's repeated to the left, upward and downward, in front and behind. We have lots and lots of these cubes. So every chlorine atom is surrounded by 6 sodium ions, and every sodium ion is surrounded by 6 chloride ions, but this is the real form of sodium chloride. They are touching each other, not separated. Now we want to think about the strength of ionic bonding. Do all the ionic bonds are similar? Are they all similar? Are they all having the same strength? If I draw a magnesium oxide, is it the same strength as when we draw sodium chloride? This is not the case. This is not true. We will find that the strength of the ionic bonding depends on 2 factors. It depends on the size of the ion, and also it depends on the charge on the ion. For example, if we take here, we are going to find out the strength of ionic bonding in case of lithium fluoride, lithium chloride, lithium bromide, lithium iodide. We will leave lithium to be constant for all of them, and we are going to change the negative ion from fluoride to chloride to bromide to iodide. Of course, we know that these are the inert gases, and these are their ions. We are going to compare the strength of lithium fluoride ion by lithium chloride, by lithium bromide, by lithium iodide. Of course, to compare the strength, we have to find out about how much energy is needed to break a bond. For example, if I have lithium with fluoride, I have lithium with chloride, I have lithium with bromide. This is fluoride, this is chloride, bromide. If I have lithium with iodide, so we want to see which one of them is stronger, the ionic bond. Are all ionic bonds here similar? Do they all have the same strength? We said no. This depends on 2 factors, the charge and the size. So how do we know the strength? We are going to find out how much energy is needed to break these bonds. How much energy is needed to break between a lithium ion and a fluoride ion, a lithium ion and a chloride, a lithium ion and a bromide, a lithium ion and an iodide. How much energy is needed? Of course, the more we need energy, this means the stronger will be the bond. So not all ionic bonds are similar in strength. It depends whether I have a strong bond between the ions or weak bonds. And we know this from the energy required to break these bonds. Now, if we look at the energy required to break the lithium fluoride bond, we will find it to be 1031. In order to break the bond between lithium and chloride, it will need a lower energy, 848. If we find out the energy needed to break the bond between lithium and bromide, we find it to be 803, still lower, and lithium iodide is the least. So since lithium is constant in all these compounds, in all these ionic compounds, the charge on the fluoride, chloride, and bromide and iodide is the same. It's -1. So what is the only difference is the size of the ion. The fluoride ion is small, the chloride ion is greater, the bromide much greater, and the iodide much, much greater. So as we see that as the size of the negative charge ion increases, we see that the bond between it and the lithium ion decreased in strength, and it required less amount of energy. As we go down like this, we'll find that the lithium fluoride ion needs the most greater energy to be broken, followed by the lithium chloride, followed by lithium bromide, followed by lithium iodide. So this means that as the ionic size increases, the bond becomes weaker and requires less amount of energy to be broken. And the same if we compare, if we take group 1, lithium, sodium, potassium, rubidium ions together with fluoride. We are going now to let fluoride be constant for all, but we differ in the positive ion. We will find the same trend. We will find that lithium fluoride needs the most energy to be broken, followed by sodium fluoride, which has a bigger radius than that of lithium ion. Potassium ion has a bigger radius than sodium ion, so it requires less amount of energy to be broken. Rubidium ion is much greater than in size than the potassium ion, so we will find that its bond with fluoride ion, which is the same fluoride ion, it decreases most, which means that as the radius, the ionic radius, whether it is a negative ion or a positive ion, as the ionic radius increases, we'll see that the bond strength, the ionic bond strength, decreases. Okay, this means that whenever we have small sizes, the attraction force between the ions is the greatest. The attraction force here is the greatest. That's why it requires the biggest amount of energy to be broken. Okay, so this is the first factor, that the strength of ionic bond depends on the radius of the ions. The more the radius of the ions, the weaker will be the ionic bond strength. This is the first factor. Do you have any question before we go to the second? Okay, now for the second factor, we said the charge. If I am comparing, for example, lithium fluoride with magnesium fluoride, lithium and magnesium nearly have the same ionic radius, nearly. They have the same ionic radius. If you look here, in case of lithium ion, the magnesium ion has a radius of, this is the magnesium ion, has a radius of 0.072 nanometers, and the lithium ion has 0.074 nanometers, which means that they are nearly similar in size. But we will see that magnesium has a +2 charge, but lithium has a +1 charge. So if we are comparing the lattice energy, it means the energy required to break a lithium fluoride bond, we'll find it to be 1031. But in order to break the magnesium fluoride bond, it needs 2957, about 3 times that in case of lithium fluoride. About. This is lithium fluoride bond energy, the energy needed to break the lithium fluoride bond. It's 1031 kilojoules per mole, whereas the energy needed to break the magnesium fluoride will be 2957 kilojoules per mole, which means that this is about 3 times that, although the size of the ions are nearly the same. So this means that the second factor to be considered is the charge on the ions. If we have more charge, magnesium has a +2 charge, which is greater than the +1 charge, we'll see that the ionic bond will be stronger. Now, what if both ions, here the fluoride ion was similar, But if we have magnesium oxide instead of magnesium fluoride, we'll see that the bond strength becomes much greater. It becomes 3,791, greater than the 2,957. This is because here in both we have magnesium ions, but here we changed the fluoride ion, which has a negative charge, with the oxide ion, which has a -2 charge, which means that the more the charge on the ions, the greater will be the strength of the ionic bond. So not all ionic bonds are similar in strength. It depends on the size of the ions and depends on the charge on each ion. Okay, understand? Do you have any question? Okay. Now, how do we prove that ionic compounds contain ions? What is the proof that ionic compounds contain ions? So, of course, the proof is what we studied in O level about electrolysis. We said that if we have two inert electrodes placed in a molten, or of course here these are molten sodium chloride, and we connect these two electrodes by a direct current supply. We said that in case of sodium chloride, for example, molten, we have sodium ions and we have chloride ions. And this means that the positive ion, which is the sodium, will be attracted towards the negative electrode, which is connected to the negative pole of a direct current supply. And the chloride ion will be attracted towards the positive electrode, which is connected to the positive pole of a direct current supply. And we will see that sodium ions, when they reach the negative electrode, they will gain an electron and form sodium metal. And so we will see that there is sodium metal in the form of molten, of course, state, will be deposited here on the negative electrode. And we will see that the chloride ions would gain 2 electrons and form the chlorine. Sorry, they will lose 2 electrons at the positive electrode. At the positive electrode, they lose 2 electrons and form the chlorine gas. And we have studied that chlorine gas is a greenish yellow gas, and we can see it, the greenish yellow gas. We can see it evolving here at the positive electrode. And this will prove that sodium chloride is present in the form of ions, because if it was not present in the form of ions, the sodium will not be deposited on the negative electrode and the chlorine gas would not be formed. But they were formed because one of them gained electrons and the other lost electrons, and they formed these products. So this is an evidence that in ionic compounds, we have ions. Another evidence, which came 2 times in exams, they brought this in the exams. If we start with copper chromate, this is called copper chromate. This is the copper 2 chromate. We place copper chromate, which is green in color, and we also place it in a U-tube containing, it should not always be a U-tube, but this will show us the colors clearly, more clearly. In the U-tube, we place the copper chromate, which is green in color, and we place 2 electrodes, inert electrodes, of course, and one of them is joined to the negative electrode of a direct current supply, negative pole, and the other electrode connected to the positive pole of the direct current supply. After a while, we will see that this place will have a blue color, and this solution here will have a yellow color. And this means that the copper chromate is divided into copper ions and chromate ions. The copper ions are blue, whereas the chromate ions are yellow. And so together they had the green color. But when they are placed in a direct current supply and current is allowed to move, we will see that the copper ions will be moving towards the negative electrode. That's why they are collected here, forming the blue color, whereas the chromate ions will be moving towards the positive electrode, where the yellow color appears here. And this also proves that ionic compounds are formed from separate ions. Okay, As I told you, this came twice in exams, the chromate experiment. When we try to draw what we call a density map, they will always ask you about these electron density maps, especially in multiple choice questions. They will give you what we call, or sometimes even in structured questions, they say draw the electron density map. So we are going to express the ionic compounds in what we call an electron density map, and also in the covalent compounds. But here we are studying ionic. So this electron density map shows us that the sodium ions and the chloride ions, this represents the sodium ions. This electron density map represents sodium ions, and this one represents chloride. This represents chloride, and this represents sodium ions. We'll see, of course, that they are represented, we call them electron density map. It means that we show electrons in the form of circles. You don't have to know the number of these circles. You can draw any number of circles. The only thing you have to notice that these circles of sodium ions are separated from the circles of the chloride ions, because in covalent compounds, we will see that they merge together. But here in ionic compounds, they are separated. Always we draw the negative ions having a bigger size than that of positive ions. So this electron density map represents the electrons present in sodium ions and chloride ions. We only draw them as separate, and we show that the negative ion is greater than the positive ion. This is called the electron density map. Sometimes they will ask you to draw electron density maps in the exam, or sometimes they bring it to you in the form of multiple choice questions. So for ionic, they are separated because, as I told you, in covalent compounds, we will see that they merge together. So they have a different structure, and they should be separated. And we draw the negative ions greater than the positive. And this shows that within the ionic compound, we don't have only one sodium ion and one chloride ion, but we have lots of positive ions and negative ions. And all the ions together are attracted to each other by the electrostatic attraction force. Not only one sodium attracted to one chloride. No, this sodium ion is attracted to all the chloride ions around it. The one above it, the one below it, the one beside it, the one in front of it, the one below that comes afterwards it. All the sodium ions are bonded to all chloride ions. There is a very strong electrostatic attraction force between the ions. Okay, we call this the electron density map. Do you have any question till here?
Miss?
Yes.
For the circles within the actual ion, do you have to draw a specific number, or is it?
No, you don't have to draw any specific numbers. You have to draw any numbers you want.
Okay, thank you.
Okay, you're welcome. Now we come to what we call polarization of ions. The ionic radii and polarization of ions. Now let's talk before the polarization of ions. We will talk about trends in ionic radii. What happens when we say trends? What happens as we go down a group for its ions, and what happens as we go across a period for its ions? Now, if we look at down a group within a certain group, for example, if we are talking about group 1 ions, for instance, we'll see that lithium has 3 electrons. At the beginning, it was 2, 1, and then sodium had 11 electrons, so it was 2, 8, 1. Potassium has 19 electrons, so it was 2, 8, 8, 1, and so on. Now, when they form ions, they will lose this outer electron to form the ions. But still, lithium has only one shell in case of ions. If we talk about the ions, the lithium has only one shell. When it lost this outer electron, it had only one shell containing the 2 electrons. When sodium lost this outer electron, now it has 2 shells containing its electrons, 2, 8. Potassium ions, when it lost this outer electron, it had 3 shells, 2, 8, 8, and rubidium, when it loses its outer electron, it will have 2, 8, 18, 8. But still, since we said in case of atoms, as we go down the group, the atomic radius increases as more number of electrons are present and more number of shells. The same will be said here for ionic compounds. All what happened is that the outer electron was removed, but the number of shells is still increasing as we go down the group. You will see here that lithium has only 1 shell, sodium ion has 2 shells, potassium ion 3, rubidium has 4. So the ionic radius increases as we go down the group, due to the presence of more number of electrons, the presence of more shells to be filled. And the same happens for negative ions. If we take group 7 as example, fluoride, chloride, bromide, and iodide, all of them gained an electron. But from the beginning, the fluorine atom had a smaller radius than the chlorine. The chlorine has a smaller radius than the bromine. The bromine has a smaller radius than iodine, which means that as we go down the group, the atomic radii also increased. Also, in case of their ions, they only accepted 1 electron each. So this electron will be placed in the last shell. But also, we'll see that as we go down, the ionic compounds, the ionic radii increases. So here the fluoride ion has the smallest ionic radius, followed by the chloride, bromide, and iodide. This is 0.133, this is 0.18, and so on. It increases. It is also due to the increase in the number of electrons and the number of shells. Okay, so whether we have any group, whether it is a metal or a non-metal, always the ionic radii will increase as we go down the ions, as we go down the group for ions. Now, what happens in case of periods? If we start with, for example, period 3, containing sodium ions, magnesium ions, aluminum ions. In case of sodium atom, it had, as we said before, 11 protons and 11 electrons. But if we have sodium ion, what happens? The number of protons is the same as in case of sodium atom, but the number of electrons decreased by 1. And we said before that whenever we have more protons than more electrons, if there is a certain attraction force between these 11 protons and 11 electrons, when the electron number decreased, then the attraction force between these 11 protons and these 10 electrons will increase. And when it increases the attraction force, this means that the 11 protons will pull the 10 electrons more than the pull between the 11 protons and 11 electrons. And this means that the radius, if I compare sodium atom by sodium ion, the sodium ion has a smaller radius than that of sodium metal. If we compare positive ion with the metal itself, we'll see that the sodium ion has a smaller radius than the sodium metal. Now, what if I compare sodium ion by magnesium ion? In magnesium, it has 12 protons, but it still has 10 electrons because it lost its outer 2 electrons. At the beginning, magnesium, at the beginning, it had 12 protons and 12 electrons. But when it loses these outer 2 electrons, it will have 12 protons and 10 electrons. Now, I'm comparing sodium ion with magnesium ion. Here, in case of sodium ion, there are 11 protons pulling 10 electrons. In case of magnesium, it increased the number of protons. It's 12, but the number of electrons are the same, 10. So what do you think? Which one will be more attracted? Which one, the electrons of it will be more attracted to the protons? In case of sodium ion or magnesium ion? Yes, excellent, Yamal. Of course, in case of the magnesium ion, the electrons are more attracted towards the protons, because here we have more number of protons. It will pull these 10 electrons more. That's why we will find that the radius of magnesium ion is smaller than the radius of sodium ion. Also, if I compare aluminum that forms +3, it has 13 protons, but we have also 10 electrons because aluminum lost 3 of its electrons. So 13 protons are pulling the same number of electrons. We call these ions, we call them isoelectronic. You will always see this word in exams, isoelectronic. Isoelectronic means they have the same number of electrons. All of them have 10 number of electrons. So we call them isoelectronic ions. Isoelectronic, it means they have the same number of electrons. So as long as the number of protons increases, the attraction force towards the electrons will also increase and the radius decreases. So the ionic radius of a +3 ion will always be in isoelectronic. It is going to be always smaller than that of the +2 and the +2 smaller than the +1. If we compare the ions, the negative ions in case of period 2, nitride, oxide, and fluoride, we'll find the same happens. In case of nitride, we have, in case of nitrogen, we have 7 protons and we have 7 electrons. But when nitrogen have 3 electrons to form the nitride ion, it gains 3 electrons. And so it will have 7 protons, and now it will have 10 electrons. So it is isoelectronic also with the positive ions because it contains the same number of electrons. So here the protons are 7 pulling 10 electrons. In case, of oxide, in case of the oxide ion, we have 8 protons pulling also 10 electrons. In case of fluoride ions, we have 9 protons pulling 10 electrons. And of course, the attraction force between 9 protons and 10 electrons will be greater than the attraction force between 8 protons and 10 electrons, greater than the attraction force between 7 protons and 10 electrons. That's why we will see that the fluoride ion will be the smallest radius, followed by oxide and nitride. Nitride has the greatest radius. The more the number of negative charge, the bigger is the radius. But the more number of positive charge, the smallest is the radius. All these tricks are called isoelectronic, and they usually bring this in the multiple choice questions to compare between the sizes of positive and negative ions, which are isoelectronic. They should be isoelectronic. For isoelectronic, we will see that the more the positive charge, the smaller will be the radius. But the more the negative charge, the bigger will be the radius, because the number of electrons exceeds the number of the protons too much, and that's why the attraction force is the smallest, and it will have the biggest radius of all, of course. This is the smallest radius of all, and this is the biggest radius of all. Do you have any question? Do you have any question? Okay, now we come to an important thing, which is called polarization and polarizing power. Now, we are talking about ionic compounds, and we said that the attraction force between the positive and negative ions depend on the sizes and depend on the charge. But now we are going to talk about something else, which is called polarization and polarizing power. And it's a very important topic. Why? It's not, I didn't say that it's hard. I only said that it is important because in Unit 2, inshallah, you are going to study about the decomposition of ionic compounds like carbonates and nitrates. And the decomposition of these nitrates and carbonates depend on this property, which we call the polarization and polarizing power. Now, what is polarization and polarizing power? Now, if we take, for example, in a certain ionic compound, for example, if I'm comparing, for example, lithium ion by, for example, sodium ion, I'm just drawing it bigger to show you. Of course, it's not too much bigger, but in order to show you that what happens here, this is lithium ion, and this is, for example, chloride ion, for example. if I'm comparing lithium chloride by sodium chloride, we'll see that in case of lithium, both of them, lithium ion and potassium ion, both of them has only one positive charge, but we will see that the radius of sodium ion is greater than the radius of lithium ion. Chloride ion is the same. Now, what happens when we have a small radius, of course, and a big charge? It would be in the big charge, but now I'm comparing a small radius. If I have 4 cation means the positive ions. If we have a small radius and a big charge, we say that the polarization power increases. The polarization power of, for example, what we have as a small radius and a big charge, the polarization power is greater, increases. For anions, which is the negative ion, the bigger the radius, big radius and big charge will be more polarized. Will be more polarized. What do we mean by polarization and polarized? Polarization means that it can pull the electrons of the negative ions towards itself. If we draw them separated to show how electrons are pulled, for example, if I have here a negative ion, if I draw it separated away from the positive ion to show how electrons. Now here we have a negative ion. So the smaller the radius of the positive ion, and of course, if much better to command have a bigger charge, we will see that this positive ion has the ability of the capability of pulling the electron cloud or the electrons. We call the electrons electron cloud. It has the ability to pull the electron cloud or the electrons of the negative charge towards itself. So we will see that if we compare lithium with sodium ions, as lithium ion has a smaller radius, we don't have, of course, a big charge. Both of them are similar. So if we have a smaller radius, this means that the positive charge is concentrated on this small radius, and it will have the ability to pull the electrons of the negative ion towards itself. And we say that this is called polarization. The lithium ion has a bigger polarization power than the sodium ions. Polarization power means the ability to pull the electrons of the negative ion nearer to itself. So we call this polarization. And if the ion has a negative charge, of course it has a negative charge, but I mean it has a bigger radius. The more the bigger radius, it will be more easier to be polarized. The more it has a bigger radius, the more it will be polarized. Okay, you understand what's polarization power and what is polarizability of negative ions? If you see here in this drawing, you will see that here are the cations and here are the anions. Polarization power of the cation means that it has the ability to pull the electrons or to pull the electron density of the negative ions towards itself. And electrons will be formed here. Electrons will be attracted to the positive ion in this place. And in that case, we say that the ionic compound is not 100% ionic. It will not be 100% ionic. It will have what we call a considerable covalent character. It will have a considerable covalent character. What do we mean by considerable covalent character? It means that it will not, it's still 100%, it is still an ionic compound, but not 100% ionic. It has some properties of covalent character. And this is because the positive ion pulled the electrons or attracted the electrons of the negative ion towards itself. So as if they have a covalent character, because electrons are pulled in this place between the two ions as the covalent bonds form. If you remember from O level, the covalent bond is formed when the electrons are shared between two atoms. They are present in between the two atoms. They are present here in between the two atoms. And when they are present in between the two atoms, they form what we call the covalent bond. So here, if you look here in this ionic compound, although it is ionic, but it has what we call a considerable covalent character. It has a small amount of the properties of a covalent bond, because electrons, when they were pulled, they are present now here in between the positive and the negative ions, as if they are present here in a covalent bond. And of course, the polarization power increases when the charge density increases. The charge density is the charge over radius squared. So the more the charge, the more we have a +2 charge, a +3 charge, it will have higher charge density and higher, of course, polarization power. And the smaller the radius also means that we will have a charge density, a high charge density and a high polarization power. And on the opposite, if the anion has a high charge and a big size for the anion, it will also be more polarized towards the positive ion. It will be more attracted towards the positive ion, and this will cause a considerable covalent character in the ionic compounds. Understand? Well, do you have any question? Yes. The charge density, it has no definition. It's just a formula that the charge density equal charge over radius squared. The charge density is equal to the charge over the radius squared. The more the charge and the smaller the radius, the bigger will be the charge density, and the bigger will be the polarization power of the positive ion.
So is it related to the polarization power?
Yes, yes. The more the charge density, the bigger will be the polarization power of the positive ion.
Okay, thank you.
You're welcome. Do you have any question? Also, as we said, that the higher the charge on the negative ion, and this is the high charge and bigger radius for anions. It's not small radius. When we have for anions a big charge and a big radius, it will be more polarized towards the cation. I think this is not correct. High charge and small size of anions, no. Anions with large charge and mafud with large size, as it is written here. This is the correct one. No, ya Omar, they cannot. Always, Omar is asking, can anions polarize cations? No. It is the cations that always polarize the anions. The cations are always pulling the negative ions and not the opposite. Because in negative ions, they have the electrons in excess. Because they are anions, it means that they are having negative charge, they're having more electrons, and these electrons are pulled towards the cation. But the cation is having less number of electrons than it is supposed to. Positive ions means it lost its electrons, so there are no electrons to be pulled towards this has a positive charge pulling the negative, but the opposite will not take place. Okay. Do you have any question? Any question? Okay. Of course, we come to do you have any time to talk about the physical properties of ionic compounds? Of course, ionic compounds have high melting temperatures because we said that the electrostatic attraction force between the positive ions and the negative ions is too strong. And so it requires a big amount of energy to break the bond between the positive ion and the negative ion. That's why all ionic compounds, as they have giant ionic structure, they have high melting temperatures required to break the bonds between all these positive and negative ions. All ionic compounds are brittle. What do you mean by brittle? Brittle means that if you knock it with anything, if you have a crystal, for example, of sodium chloride, and you knock it by anything, it's going to be cracked. It's going to be cracked into smaller sizes. We call this brittleness. It can be cracked when you apply any stress, So that's because in an ionic compound, as you see, we have positive, negative, and this positive and alternating positive and negative holds the ionic compound very strongly together. But if you apply any stress, you knock it by anything, then these layers of positive and negative ions will slide by this stress. These layers slide, and when they slide, as you see, negative ions come next to each other, so they will repel. When they repel, this means that they are cracked, that the sodium chloride crystal will crack, because whenever we have negative ions in front of each other or positive ions in front of each other, they will repel. So this part will go in a place and this part will go in another place, and they will separate. There is also electrical conductivity, as we know from O level, that the ionic compounds, when they are in the solid state, they do not conduct electricity because there are no moving ions. But when they are present in the molten or aqueous state, they can conduct electricity because now they have moving positive and negative ions. For conductivity to take place, electrical conductivity, there must be moving ions or moving electrons. In case of ionic compounds, when they are in the solid state, they do not possess any, they do not have any moving ions. But in the molten or aqueous state, they have moving ions. Of course, most of the ionic compounds are soluble in water, because when they are present in water, the water molecules will enter in between the positive ion and the negative ion. It's going to separate them, and the water will surround the positive ion by its oxygen part. This is a water molecule. The red one is the oxygen, and these are the hydrogens. So we will find that water comes in between the positive and negative ions, and it will surround the positive ion through its oxygen and surrounds the negative ion by its hydrogens, which are positively charged. And we call this hydration. Hydration means surrounded by water molecules. And they form a new bond between the positive ion and the water molecules, and between the negative ion and the water molecules, a new bond is formed. We call it ion dipole bond, but of course you don't have to know this. But we know that most of the ionic compounds, when they are present in water, they dissolve in water. But of course, some do not. So these are the physical properties that we have to know about ionic compounds. Do you have any question for today? Do you have any question? Type. Okay, thank you so much, and see you inshallah next Thursday. Bye-bye.